Hello, my name is Morgan Kline, and I'm currently a fourth-year mechanical engineering undergraduate student here at Michigan Tech. I'd like to talk a little bit about my research project from last summer in 2020 under Dr. Gordon Parker. So my research specifically was, it pertained to the optimization of wave energy converters through neural networks. So if we look at figure 1 here, this is a wave energy converter. So what we typically call them WECs. And what WECs do is they convert kinetic energy that is readily available in large bodies of water, and it converts it into useful electrical energy. So as you can see, there's a drag plate and the buoy and generator inside. And when waves hit this buoy, there's a relative motion between the drag plate and the buoy because the drag plate stays primarily stationary. And this is the kinetic energy that is converted into electrical energy. Most of this energy is stored. However, you can actually maximize your energy extraction if you do something called impedance matching, and you release a little bit of energy back into the generator at opportune times. In order to do this, so by doing this, what you're really doing is you're artificially manipulating the natural frequency of the buoy to maximize this energy output. And in order to do this, you really need to know the future excitation force. You need to be able to predict that based on current wave conditions to find what you need to be doing with your PTO force. So I can elaborate on this in WEC dynamics. So here's the equation of motion for a point absorber WEC. And as you can see, the sum of the forces is equal to the excitation force, the radiation damping force, and the static force, as well as the PTO force. These two components are not very difficult to find, the radiation damping and the static force, but the excitation force is rather tricky and it requires some complex calculations, and even measuring it is quite difficult. So if we want to know what we have to do to the PTO force, we really need to know this excitation force. In order to really be able to optimize energy extraction. So as many of you know, because of the pandemic, it was kind of difficult to get on campus into the wave tank, but I was able to do a lot of my work through simulations, and I used MATLAB and Simulink software. Shown in figure 2 is an example of one of the simulations I used. This portion is this is where we created the waveform inputs. So we combined sine waves, and we ended up getting our wave gauge displacement readings, just simulated theoretical wave displacement readings at 3 different locations. So this would be at the location of our first set of wave gauges, second set of wave gauges, and then here's at the location of the buoy. And then from there, we were able to find the excitation force at the buoy and then the displacement of the buoy itself. In addition to this, I was able to explore multiple neural network methods, such as a NARCSnet, a NARNet, LSTM, and nonlinear input-output time delay network. All of these networks were fed the wave gauge displacement measurements, the buoy displacement measurements, and the target excitation measurements, and they were all asked to output the excitation force prediction. Additionally, all of these networks were tested with varying degrees of data difficulty, from linear to highly nonlinear. At the end, what I found was that the nonlinear input-output time delay network had the best results across all data difficulties. Figure 3 shows a map of such a network, and then figure 4 is the mean squared error of the output of the excitation force for the training, validation, and test process, for the most challenging set of data for highly nonlinear input data. So this network had an error of 10 to the negative 3, but with our more easy to predict data, that had an error of 10 to the negative 7th mean squared error, which are within our range, and these are acceptable for our purposes. Additionally, I found that the time delay network had a runtime under 20 seconds, which is much better than the NARCSnet and the LSTM, which had a runtime of a few hours. So in conclusion, the wave tank team is currently making a force measurement unit to measure forces directly on the buoy so that we can find this excitation force and really test the validity of the results of this network. So thank you for listening, and I hope you have a great day.